So today we're going to be calculating equilibrium moles using either data which is just moles or equilibrium constants, which we looked at last week. To start with, you'll find on Satchel a Kahoot link to an equilibrium and KC quiz. So start that first before you proceed. Now, recapping last week's lesson, we met the equilibrium constant. K equals C to the power of C, D to the power of D, A to the power of A, B to the power of B. Those square brackets are essential. They show that that's concentration we're looking at, and they're all to the power of the stoichiometry coefficients. There's the number of moles there are of each thing. You guys were great at this last week and working out units also. So, we met this concept in lessons last week of calculating equilibrium constant, and we're going to use something called ICE, so looking at the initial moles, how much those moles change, and what they have at equilibrium. Sometimes you'll see it called rise to, the R would stand for the reaction. So when calculating equilibrium moles, there's a general format we can use every time, and we can set it up like this table shows here. So we have our reaction at the top, and underneath we note down our initial amounts that we have in moles there. Quite often A and B will be some number and C and D will be 0, for example, because we don't have any product at the start of the reaction. We then note down the change in those moles. Quite often for A and B that will be negative because they react to form C and D, and the values C and D will be positive. And then in the bottom row we have the equilibrium, so the values that are present in moles at equilibrium. So normally we know an initial and we know a final value. We use that to work out the change. So it doesn't make much sense, probably looking at a table by itself. So we're going to go through a few different examples today. I recommend you write or print out the question that we're going to be looking at and have a table ready. I'm going to colour coordinate each step, so if you've got 5 colours handy, it'll make it really helpful for you to see how you approach this question. So, in this example, a mixture is prepared using 2 moles of A and 1.5 moles of B at a given temperature. The mixture is left to react according to the equation 2A plus B goes to 3C plus D. The equilibrium mixture, so after we left this for a period of time, contained 0.7 moles of B. Calculate the amount in moles of A, C and D in the equilibrium mixture. So, have your table written out, have your question written out before you move on. So, step 1, let's write down the initial values. We had 2 moles of A, 1.5 moles of B. We didn't have anything of C and D, which would be pretty typical. So, let's have a think. Was there any other information we were given that we could add to this table? So if you look back over the question, we can see we were told how much of B there was in equilibrium mixture. So we add that value in, that was 0.74. Now, if we know how much we started with B and how much we have in the equilibrium mixture, we can work out how much B has changed. So we can work out then that the change in B was minus 0.76, and we can put that on our table. Now that represents how much of B, how many moles of B have actually reacted with A to form C and D. And that's a really helpful number to use, because that number is the number of moles B reacted. We know, because of the ratios of that balanced equation, how many moles of A is reacted with, how many moles of C is produced, and how many moles of D. So if we put these numbers in, A will have dropped by 2 times 0.76, so minus 152. C will have increased by 3 times 0.76, and it's positive because it will have gone up, and D will have the same number of moles that it reacted, so that will be plus 0.76. So with that we can work out what moles were present at equilibrium. So for C and D, that's nice and straightforward. 0 plus those values, give those values on the bottom row. And for A, we just do 2 minus 1.52, and we're left with 0.48. Now what is great is now we have those number of moles at equilibrium. What we will do is that later on is we can work out the Kc constants for this reaction. For the time being, I just want you to practice doing those first 5 steps we've just looked at. So over to you. I'd like you to fill in this table for this reaction. So we have hydrogen, nitrogen reacting to form ammonia. So classic Haber process here. A mixture of 10 moles of nitrogen and 25 moles of hydrogen were allowed to react and come to equilibrium at temperature T. We have our reaction there. At temperature T, there was a 2.8 moles of nitrogen in the equilibrium mixture. Calculate the amount in moles of hydrogen and ammonia in the equilibrium mixture. So, do those steps we did last time, pause the video, and I'll go through it when you're ready. So, step 1, you should have put in those initial values. Those were 10 and 25, and we didn't have any ammonia at the start of this reaction. You were told at the end of the experiment, or in equilibrium, that there was 2.8 moles of nitrogen. So we could see that change in ammonia was minus 7.2. Well, there are 3 moles of hydrogen, so that should have dropped by 3 times 7.2, so hence minus 21.6 there. And the ammonium would have gone 2 times that 7.2, so plus 14.4. And you can see our equilibrium values there. Hopefully you got those correct. So, final question today, question 3. And I really want to encourage you to make sure you've got the question written out and making sure for your own notes you're writing down the order that you're approaching these steps in. Because once you have these tables complete and you look back over them, it can be a bit confusing about how you filled those out. So do make those extra notes, especially in these first few times we're doing these questions, for yourself to help with your notes. So this question, the following equation was established in a closed container. 2p, forward backwards, r plus 2s. 7.5 moles of P and 2 moles of S were placed in a closed container and allowed to come to equilibrium at a certain temperature. Now we keep talking about certain temperature, that's because Kc values are only valid for a particular temperature, and we've got a closed container because that is the condition required for dynamic equilibrium. Anyway, 5.04 moles of S were present in the equilibrium mixture. Calculate the amount in moles of P and R in the equilibrium mixture. Pause the video, have a go by yourself, then I'll go through it when you're ready. Hopefully you have a table that looks a little bit like this one. So we were told our initial values were 7.5 of P and 2 moles of S. So this one we were given a reactant and a product, but we didn't have R there. So we were told at the end that we had 5.04 moles of S. So we could see that that one went up by 3.04 moles. That's because of the 2:2 ratio is the same value but negative for P, and then R is going to be half that number. That's going to be positive because that's gone from 0 initial and has increased. And then we can work out 7.5 minus 3.04 gives us 4.46 moles of P at equilibrium. The R 0 plus 1.52 gives us 1.52 moles at equilibrium also, and we were told what S was. So nice and straightforward. So reflect on what we've just done. This is new, you're seeing this for the first time. How do you feel about that? Are you still looking, going, what have you been talking about? Is it feeling okay? Do you feel like, right, get this, I've absolutely rocked it, and I'm ready to put them into KC calculations? If you want to give yourself a bit of a challenge, you can have a go at that today. But what's really important for me is that you understand those steps we take when working out equilibrium concentrations.